I'm Cameron Ladke, and in this video report, I'll be using LabVIEW to experiment with the Fourier transform and apply it to a couple real situations. So here you see that a DC offset has a pretty direct effect in the frequency domain. The VRMS increases. And we also see amplitude increase at zero frequency. And the same is true for negative DC offsets. So in the frequency domain, right now you see the effect of a changing DC offset that's below zero. So right now it's going below 0 to -1, and you see the VRMS increasing as well as the zero frequency amplitude increasing. So we can look at the effects of leakage by looking at this 40 Hertz square wave here. So the magnitude on the Fourier graph of the 40 Hertz line is lower than its actual magnitude. And this is because the fast Fourier transform, it sweeps over a set of discrete frequencies, and we should only expect the fast Fourier transform to perfectly reproduce the amplitude of our input signal if it falls at exactly one of those frequencies. So in this case, 40 Hertz falls between two neighboring frequencies, so we see the spectral peak at 40 Hertz at a lower amplitude because it's smeared among its neighboring frequencies. Now, applying a windowing function is one of the ways to correct for this. So we see when the Hanning window is applied, the magnitude is larger. It is closer to its actual value. So the type of waveform you have also determines how much leakage there is. So here we have a square wave, triangle wave, and sawtooth wave. Now with a square wave, you see a lot of harmonics and they diminish very slowly. So a lot of the strength in that signal is spread out over the harmonics. There's leakage. And this is because the square wave is a Fourier composition of many sine and cosine waves. Some of them are very high frequency. And the same goes with the sawtooth wave. On the other hand, the triangle wave, it more closely resembles a sine or a cosine wave. And so its Fourier terms don't contribute in the higher frequency domain as much as the sawtooth and square waves. So here we see aliasing of a signal from the function generator. The sampling frequency is at 2000, and so the Nyquist frequency is 1000. Anything above that, you're going to have some aliasing. Now, when the function generator gets to 1.9 kilohertz, it looks, from the frequency graph, identical to a 100 Hz signal. The same goes with 1.2 kilohertz. And then at 2000 kilohertz, when it matches the sampling frequency, each consecutive waveform trace looks identical to the program. And so it looks like a zero frequency wave. So going back to harmonics, here we have a 40 Hz square wave. And we can see that the square wave harmonics appear at odd multiples of the fundamental frequency of 40 Hz. And the amplitudes of the harmonics decrease in proportion to multiples of the fundamental frequency. So for example, at 120 Hz, the spike is 3 times the fundamental frequency, but 1/3 the amplitude. Now at 300 Hz, we can see this effect again, with the other spikes being odd number multiples of the fundamental frequency. So in this next part of the lab, I reconfigured the LabVIEW program to allow the averaging of multiple signals. Now, pushing the limits of the DAC's resolution, we see some interesting phenomena. When the program averages very noisy signals that are very small, some of that noise and randomness gets translated into a larger and larger DC offset. And the effect this has is it makes the VRMS bigger than it actually is. It may look like an accurate reading, but it's actually larger than it should be. And we see this in the obtained data. And another thing to note is the fact that we can actually gain information about the phase of our signal from the frequency domain. And that's because if from the original derivation of VRMS, there was the A term, which was the AC term, and then there was the offset term. Now, getting the inverse tangent of those terms, the relationship between those terms, gives you the phase. And you can get those terms by analyzing the VRMS. So in the next couple of parts of our lab, we'll be studying how a device reacts to a given input stimulus, allowing us to characterize the device. Now to do this, we need a source of white noise. So that's noise that spans all frequencies. Now, in this first part, we'll be using the function generator's built-in white noise source to get the frequency response of a couple RC filters. So, testing out the white noise feature of the function generator, we see that it has the effect of giving a straight horizontal line of frequencies. So to characterize a low-pass RC filter, I hooked up the function generator to its input, and then it hooked up its output to the DAC. So here you see the frequency response of the RC filter, and we can calculate the characteristic frequency of the filter by looking at it visually or by calculating it based off of its component values. Now looking at it visually, we can find the point where the signal is attenuated to 70% of its maximum, which is around the -3 dB point. Comparing our observed 3 dB point to our calculated, the values come very close. So the next circuit we aim to characterize is a high-pass circuit with an additional low-pass component. And this is much harder to characterize analytically, but we can do it by splitting the circuit into 2 voltage dividers and then solving for the transfer function. Taking the magnitude of the complex transfer function and plugging in the component values, Then solving for the 3 dB point, which is 1 over the square root of 2, we can find the characteristic frequencies. So here we have the program running, averaging signals. Now, using the same method as with the earlier RC filter, we can visually inspect the negative 3 dB point by looking at the max and then 70% of that max. And what we see is our observed negative 3 dB point is fairly close to what we calculated. Now, in this final part of our lab, I'm going to get the frequency response of an unknown source. And instead of using the built-in white noise generator, I'm going to use a series of bursts of an impulse function. So an impulse function, as the duration of the pulse gets shorter and shorter, and it gets closer and closer to a delta function. In the frequency domain, it becomes a straight horizontal line, like we saw with the white noise earlier. So with the function generator set to 5 kilohertz, we see the waveform output of the impulse function, or it's in burst mode, so it's a series of impulse functions. Turning the function generator up, the impulse function gets narrower and narrower and more closely resembles a delta function. And so as a result, the frequency graph gets more horizontal and more closely resembles a straight horizontal flat line of just white noise. So for our measurements of the unknown source, we're going to be setting the impulse function at 100 kilohertz. So we need to look at what the maximum amplitude is at 100 kilohertz to use as reference later to see if the signal is attenuated or if there's gain. Now here we're just zooming in to measure the amplitude of the signal. So for the actual experiment, it consisted of a black box with some device inside of it, and we connected it to a voltage source, which was powering it, and then the function generator. So looking at the frequency response, it looks as if our device is a bandpass filter because you see a range of frequencies that are not attenuated, and then a lower and a higher range that are attenuated. So it lets pass a certain bandwidth of frequencies. Now, adjusting the axis in the frequency domain to be logarithmic, both axes, our Fourier plot becomes a Bode plot. And we can clearly see the flat frequency band on the top. And inspecting it more closely, you see there's 3 distinct parts. There's the parts where the signal is attenuated, the center flat region, and on the very right, the noise pedestal, where there's a jump in amplitude. Now, further inspecting the plot, we can calculate the bandwidth of our filter. So using a simplified approach, we can look at the frequency spectrum between the points where the frequency is at 50% of its maximum. And so by setting the y-axis to 50% of the maximum, the places where it intersects the x-axis are the lower and higher end of our filter bandwidth. And this is 200 hertz on the lower end to 4,000 hertz on the higher end. We can also measure the gain or attenuation of the device. So looking at the 2000 Hertz frequency and comparing the amplitude to our calibration amplitude, we see that the filter produces a very small gain of about 1.8 times 10 to the negative 5 volts. Now, finally, by measuring the amplitude difference between two frequencies that are an octave apart, we can measure the attenuation in decibels per octave. So yeah, that's the end of the lab, and here's a cool animation.